most people involved
looking
in searching for extraterrestrial intelligence,
from an alien civilization.
The
telescope was
was
significant amount of telescopes
one
have
of
been
two
in
signal
never to
scenarios.
be explained.
Science always seeks the unknown for answers that we don't understand yet. Why did Columbus sail across the ocean? To see what's there and discover other peoples or other lands. Are we alone in the universe, or is there really other intelligent life out there?
The question of intelligent life is really a big question because it goes beyond just having biology. It's biology that got clever enough to understand the universe.
If there are other civilizations out there, we automatically know that all the questions of life are answered yes.
If we did discover an actual signal from an alien civilization, it would profoundly change human beings.
This is discovery. It isn't the kind of science you learn about in middle school where you have an hypothesis and you try and falsify it. You can't falsify this hypothesis. You can't prove they're not out there. All you can do is discover that they are.
So we have these 50 digits, so it looks like a bunch of random numbers.
62UJ5, that was exactly what we were looking for.
I don't think many people have looked into it in much detail.
It's an intriguing case because it's a mystery. We don't know what it was.
It was the strongest signal I ever saw.
An enormously powerful signal.
It is the best evidence we know of coming from some other civilization.
Why do we search? Mankind has always been fascinated by the possibility of life beyond Earth. The idea of other civilizations thriving on distant planets captivates the imagination. We are driven, perhaps, by the hope that humanity is not alone in the universe, and by science's promise to always seek the unknown. On August 15, 1977, a massive radio telescope operated by The Ohio State University detected an unusually powerful signal from deep space. The signal had all the characteristics scientists expected in a transmission from an intelligent extraterrestrial source. The event lasted for 72 seconds and was never heard again. Named the WOW signal, it was a tantalizing moment in the search for extraterrestrial life and for the relatively young science of radio astronomy.
Started going up and went 6EQUJ5 as it faded up to the other side. That's just a tremendously strong signal. We'd never seen anything like that before. And that told us that this really is a very strong narrowband signal that did not come from some natural source.
Most are familiar with the traditional science of optical or visible light astronomy. Optical telescopes capture light rays and magnify distant objects for closer observation by the human eye. In comparison, radio astronomy focuses on the invisible, the radio frequency portion of the electromagnetic spectrum. Radio telescopes are specialized antennas and radio receivers that can detect the radio waves emanating from distant celestial objects.
Every object that produces energy, every star, every galaxy, produces energy all along the energy range, which we call the electromagnetic spectrum. The trouble with a visual telescope is that it only looks at a part of that spectrum, why I have one right here, that is very narrow and a very small part. We actually see a very small part of the universe. On one end, you have the higher energies, like ultraviolet and X-rays and gamma rays. On the lower end, down below the red, you have the very low frequency energies like infrared and radio. This is very, very narrow. It happens to be the part we're interested in because it's the part that we can actually detect. So you can look at a lot more information about a star at the radio end of the spectrum than the very limited amount of information you get in the visual end of the spectrum.
Although radio waves from space were first detected in the early 1930s, and the first radio telescope was built shortly thereafter, worldwide interest in radio astronomy escalated in the years following World War II. The United States was eager to invest in this new branch of science.
We were kind of in the space race. We were in this idea that our country wanted to be the best in the world in terms of science and engineering. We wanted to be out there, and we were willing to spend a lot of money, frankly, to do that. So we spent a lot of money. We got men on the moon. We built telescopes. We built a lot of fundamental science facilities here in the country. And that was fantastic, and that just led to so many advances.
You know, after World War II, there was a lot of technological achievement, especially in electronics and with radar coming on the scene and all of that. But, you know, the war took its toll, you know, on most of the nations. But for whatever reason, Europe, especially England and Australia, really ramped up radio astronomy research. The United States didn't. They kind of lagged behind until about mid-50s. Part of the reason was that instruments to detect radio signals from space are just so expensive to build. You know, a single university generally can't afford to build what you need to build to be successful.
As radio astronomy continued to evolve, a young professor of electrical engineering at The Ohio State University observed its development with keen interest. His name was John Kraus. In the 1930s, Kraus followed scientist Carl Jansky's historic discovery of radio noise flowing from the center of the Milky Way galaxy. He was fascinated by the potential for using cosmic radio waves rather than visible light to observe the universe.
In 1930, essentially all that we knew about the heavens had come from what we could see or photograph. Carl Jansky changed all that. A universe of radio sounds to which mankind had been deaf since time immemorial now suddenly burst forth in full chorus.
During World War II, Kraus met Grote Reber, a radio engineer from Wheaton, Illinois. Reber had continued Carl Jansky's work, scanning the Milky Way with a homemade receiver and a 30-foot dish antenna built in his backyard. For a decade, he was the world's only active radio astronomer, producing the first maps of the radio sky. His antenna design was the forerunner of modern radio telescopes.
He told me about his equipment and observations of the Milky Way with a contagious enthusiasm. If we had not been at war, I think I would have started building a radio telescope then. But it was not until 10 years later, at The Ohio State University, that I had a chance to do it.
When John Kraus joined the Ohio State faculty in 1946, he invented the helical antenna. The unique corkscrew-shaped design would ultimately find widespread use in satellite communication. In 1952, Kraus utilized the new antenna design to build his first radio telescope. With the help of Ohio State students, he constructed a 50-meter array of helical antennas on university farmland. While a sky survey conducted with the helix array proved successful, Kraus realized that a much bigger telescope was needed. Within a few years, he was ready to build the massive radio telescope that would ultimately capture the WOW signal.
He had grand plans of making the telescope 2,000 feet wide. Money for that was not forthcoming, so I saw at one point he had reduced that to 720 feet wide. Money was not forthcoming, so he reduced it to 360 feet wide for the paraboloid.
In 1956, John Kraus negotiated an agreement to utilize a 20-acre site owned by Ohio Wesleyan University. The property was dedicated for the construction and operation of the Ohio State University Radio Observatory. This large radio telescope, designed to listen for signals in deep space, was appropriately nicknamed the Big Ear. With a grant from the National Science Foundation, Kraus began construction on the Big Ear in late 1956. Under his supervision, university students did much of the construction work. Ultimately, the process took 5 years.
When John Kraus got the money to build the place, he didn't have very much money, so between 1956 and 1963, they constructed this gigantic thing as big as 3 football fields, with the use mostly of volunteer helpers and graduate students, so it took a long time.
The design of Big Ear was intended to be the most sensitive telescope for the least amount of money. And it was John Kraus's original design that did that.
There was only one other telescope in the world that was built like it, and that was in France, Nancy, France.
And if you can imagine here a large flat surface of aluminum foil, 3 acres in extent. At one end was a curved parabolic reflector standing on the ground. On the other end was a flat surface tilted up like this, which could be tilted up and down. And out in the middle of the ground plane, there were some things that we call feed horns that looked like scoops, which were pointed toward the parabolic part, and they scooped up the radio waves. Signals came down from the sky, they bounced off this flat reflector, traveled horizontally across this big field of aluminum to the parabolic reflector, which focused them down to these scoop-like horns sitting in the middle of the ground plane.
Unlike today's parabolic dish antennas, the Big Ear could not be electronically controlled to pan the sky on demand. Rather, it depended on the rotation of the Earth.
The telescope could not steer in the left-right direction. We could only steer in the up and down direction. But that's okay, because we could set to a certain angle and then allow the Earth to turn. And as the Earth turned, then the beam swept out a little strip all around the whole sky in 24 hours as the Earth turned. And we'd sit there for a couple days, and then we'd change the angle slightly and cover another little stripe all around the whole sky like that. So in that way, we could cover the whole sky.
When completed in the early 1960s, the Big Ear was one of the world's largest radio telescopes. It was designed to be a versatile survey instrument, capable of observing large sections of the radio sky.
When it was finally built, using its old computer with 16K of memory to help collect the data, they managed for the next 10 years to do a map of the entire visible sky.
I came here in 1963 as a graduate student working for Professor John Kraus. I was placed in charge of analyzing the data coming from our radio telescope, which had just gone on the air. We were looking for natural sources of radio signals, not intelligent sources. That's why the telescope was built. This was in the early days of radio astronomy, when it was just really getting established as a mainstream science. And there had not been any big survey of the entire sky to discover all the radio signals that were there. People had used dish antennas. They've used antennas like that to look at certain stars, certain galaxies, and study them in detail. But nobody had searched the whole sky. So we were like the pioneer explorers. And we created this huge catalog of 20,000 objects, and we published huge maps showing what the sky looked like to the radio telescope.
They discovered objects like quasars and observed them, which at the time were the most distant objects ever observed by any telescope. One of the quasars, for instance, was about 12 billion light years away, which we now know is considerably far back, almost to the beginning of the creation of the universe in the Big Bang.
They discovered 20,000 radio sources. Only 10,000 were known at the time, so it was a big deal, a big contribution to what was known in radio astronomy.
You guys want to go down to the scope?
Yeah, are we going up?
Yeah, you want to?
I guess.
Got shoes. Your shoes
I've
are
got the right
right.
shoes.
Dawson, all right back.
Why do we search for ET? Ever since the beginning of human history, we've always looked out what's out there.
The Greenbank Observatory is important to this area. It's one of the premier science facilities in the state of West Virginia. And as far as radio astronomy goes, it's one of the premier observatories in the world. You know, it's a treasure.
Nestled deep in the hills of West Virginia, the Greenbank Observatory is home to the world's largest, fully steerable radio telescope. The site hosts 8 radio telescopes and more than 60 years of scientific discovery. Like the Big Ear Telescope in Ohio, the Greenbank story began in the late 1950s. America's interest in radio astronomy was growing. The Greenbank site was chosen for building the first National Radio Astronomy Observatory in the United States.
If you look back historically, coming out of World War II in particular, there was a lot of interest in radio waves and radio technology, and of course the beginnings of radio astronomy got started. So people started listening to the cosmos, listening to the sky. And if you move forward up into the 1950s, late 1950s by then, you had radio astronomy was an actual science. There was places around the world that were studying radio astronomy. Certainly if you look over to Europe and Asia, Russia was already building significant radio telescopes at the time. The Netherlands was already building significant other radio telescopes, and other countries were starting to look at it. Within this country, although radio astronomy was acknowledged as a field of science, there wasn't any significant radio telescope that the astronomers could use. Instead, there was a lot of fantastic instruments, but kind of built in people's backyards, built in people's laboratories.
So in 1956, they started searching for a place to put this new National Radio Astronomy Observatory. And there were a lot of criteria. I mean, radio astronomy is a very sensitive science. The signals are very weak, so you had to look for a place that didn't have a lot of people. You know, people are noisy, and they build things that are noisy, especially in the radio spectrum. So they wanted a low population area. They wanted it to be free of things like overhead high tension power lines, because those things can create noise. And, you know, several other criteria that scientific staff sort of shortlisted to about 29 sites up and down the East Coast. And it turned out that Greenbank, West Virginia, was the ideal or most ideal place. So in 1957, the Greenbank site was dedicated, and we started building telescopes.
As telescopes began to rise from the ground up, the advantages of having a National Radio Astronomy Observatory in rural West Virginia quickly became apparent. Greenbank soon attracted professional radio astronomers, including those interested in a new subset of astronomy, the search for extraterrestrial intelligence, also known as SETI.
The reason a lot of astronomers came here in the early years of NRAO is, first of all, we were building the biggest and the best instruments in the world. And we were pushing the boundaries of what we knew radio telescopes could accomplish and radio receivers could accomplish.
One of the best things that happened when the idea of a National Radio Astronomy Observatory was first decided was this idea of radio quiet zones. So now you have a piece of land that's beginning to build a lot of radio telescopes, and you have legal guarantees around it that you're not going to see a lot of noise like you would anywhere else that might build a radio telescope. As soon as you have those two pieces, you have a very obvious location to come if you want to go look for weird signals, frankly. You don't want to do that someplace where there might be a lot of other noise that you have to find it through. And so the existence of a National Radio Astronomy Observatory combined with the radio quiet zones around here made this a perfect place for a lot of radio astronomers to come, including Frank Drake and many of the other pioneers of radio astronomy in this country.
Dr. Frank Drake, a radio astronomer regarded as the father of modern SETI, was a young staff astronomer at Greenbank in 1960. He devised an experiment using interstellar radio waves to search for signs of intelligent life on distant planets. Drake called his experiment Project Ozma. Conducted with one of Greenbank's 85-foot telescopes, it was the first modern search for extraterrestrial intelligence.
It was an experiment to literally go out and listen. Let's go see if we can find signals from another intelligent life out there. So in this particular case, Project Ozma was using radio waves, so the same type of technology we use today with the Breakthrough Listen project. Frank had to spend many, many hours per star to just look to get the level of sensitivity he thought he would need in order to see a signal. He pieced all of that together to just see for the first time ever, let's just go take a measurement in a very scientific manner to see if we can see a signal from alien life. Obviously, he didn't see anything. If he did, this would be a very different conversation we're having.
So this is the Drake Lounge. You can see it's furnished 1960s decor all the way, all the original furnishings and decorations. So it looks basically exactly as it did back in 1960 when Frank Drake and all his colleagues gathered here to discuss the search for extraterrestrial intelligence. Frank Drake was not the only famous scientist here. There were famous scientists from Carl Sagan to Philip Morrison. So the fun thing we always try and do is say, hey, which chair did Carl Sagan sit in? So it's sort of neat history about this place.
In 1961, following his experience with Project Ozma, Frank Drake organized a meeting at Greenbank to discuss the possibility of searching for intelligent extraterrestrial life. In preparation for this meeting, he created an equation that laid the groundwork for a meaningful scientific dialogue about finding ET. It became known as the Drake equation.
At that time, there were very few people in the world who were interested in the search for extraterrestrial intelligence. So Frank Drake being one of them, he started thinking about, what are all the factors that influence the probability of life elsewhere. So he was starting to think about things like star formation and exoplanets per star and things like that. So he thought, well, this actually fits into the form of an equation.
He just started writing these factors down and saying, this is what it's going to take. We have to know a whole lot of things, but we have to know about how many planets are there out there in the universe, for example. Of those planets, how many could actually sustain life? And you have to piece all of these factors together, and it makes an equation, an absolutely beautiful and fairly timeless equation, which is the Drake equation. What's been amazing about the Drake equation is certainly you can take a look at it now, many, many years later. It's really still the equation that you need in order to look and say, what is the probability of finding this?
L is a lifetime of a communicating civilization. We only have one example of such a communicating civilization, and that's us. So people try and estimate, how long do you think a civilization like ourselves would last? Would it last 50 years, 100 years, 500 years, 1,000,000 years? That sort of determines how many civilizations you're going to detect, because the longer they're out there, the longer they're communicating, and the more likely it is that you'll detect their signals.
What Frank did was consider a way to theorize the potential for the existence of an extraterrestrial civilization. A lot of his numbers, a lot of his assumptions were sort of proving were correct or very close to being correct. So that narrows the guesstimate factor down to a more knowing true figure. You're still talking about 100,000 potential sites that you have to look at in this huge galaxy. It still becomes a daunting task.
SETI's always been about good science. They have to make assumptions about what they're looking for. That's, a really difficult thing to do when you don't know what you're looking for. So they've always been trying to do the best science they can with the equipment and telescopes and things that they have.
SETI is such an integral part of the history of Greenbank Observatory that you can't come here as an astronomer and spend any time and not start hearing not just about what's happened here on site with SETI, but also what's happened just around the country and around the world with SETI, including things like the Big Ear Telescope, WOW signal, and all of those types of studies that have been done.
Oh, this would be some of the equipment, radio equipment that they used to modulate the data, to collect that data with a radio, essentially what we might call a radio, except that it monitors many frequencies at the same time. And just for fun, if you want to modulate some of that information and put it on a screen, you can use an oscilloscope. That's why old science fiction movies look so great, because they have those oscilloscopes running.
From 1963 until the early 1970s, Ohio State's Big Ear Telescope conducted a survey that covered 70% of the entire sky. Their comprehensive Ohio All-Sky Survey produced detailed maps of the radio sky that proved useful to astronomers throughout the world. But by 1972, budget shortages forced the National Science Foundation to terminate funding for the Big Ear. That decision closed one highly successful chapter in the Big Ear's history and began another.
In the early 70s, they ran out of money. The National Science Foundation stopped funding them. New areas of astronomy and new telescopes were being built, and that's when Bob Dixon put in a new receiver, better suited to finding the narrowband signals that people think might be out there if other civilizations are broadcasting at us.
In 1971, Bob Dixon attended a large gathering of scientists and engineers at NASA's Ames Research Center in Mountain View, California. The group shared ideas about the possibility of detecting signals from extraterrestrial civilizations. Their findings were published in a report titled Project Cyclops. The goal of Cyclops was to assess what it would take to mount a large search for radio signals from interstellar civilizations. Widely circulated by NASA, the final Cyclops report strongly influenced the development of a SETI program at the Big Ear Radio Observatory.
I became very interested in SETI at the time. Funding for the Radio Observatory nationally was lost. We realized we have a wonderful radio telescope here, and this would be a wonderful purpose to put it toward as the first large telescope dedicated to searching for extraterrestrial life. We have a perfectly good staff of people who would be willing to volunteer, and we attracted more volunteers.
I was actually a volunteer at the Ohio State University Radio Observatory. My job was as a radio astronomer, specifically looking at the computer printouts from the radio telescope.
So we had the equipment and we had the people, and we reconfigured some things and we put it together, and we started that search.
Unlike the All-Sky Survey, which had utilized wideband radio waves to search for naturally occurring signals, the Big Ear SETI program demanded a much more narrow focus.
Natural signals, they sound the same no matter where you tune your radio. If you had like your AM radio, it would sound the same hissing sound no matter where. On the other hand, an intelligent signal, we believe, will be tuned in only at one point on the dial. And that's what we're looking for, a narrowband signal. Narrowband signals are artificial. There are not very many things in nature that make narrowband signals.
The Big Ear SETI program began in December 1973. With no external funding and a volunteer staff, the program and equipment were set up to operate with as few people as possible. In just a few years, the Big Ear would make one of the most intriguing discoveries in the search for intelligent extraterrestrial life. A signal that continues to fascinate.
From what I've been told, the wow signal was a signal that came in, lasted for 72 seconds, and it looks to me like a radio source, like a real one.
On the evening of August 15, 1977, the Big Ear telescope was engaged in its ongoing mission, the search for narrowband radio signals. With its flat reflector set at a predetermined angle, the Big Ear's beam rotated with the Earth, patiently scanning a continuous strip of the night sky. Incoming radio waves were automatically processed by computer. Computer printouts provided a chronological record of the alphanumeric data for later analysis.
When we set up the receivers and the computers, we did it with a purpose of not having to have a large group of people maneuver data and do various things, because that was time-consuming, costly, and so forth. We built everything into the receiver and the computer to do things on their own.
We had, at that time, a 50-channel receiver, so we had 50 different receivers. You can imagine that 50 radios sitting on your counter, each one tuned to a slightly different frequency. And the output of all of those 50 was going into the computer we had at the time. And we had written programs to record carefully each of those 50 signals, and the intensity of each of those was then printed out on a sheet of paper. Channels 1 through 50 running across the paper.
Shortly after 11 p.m., the Big Ear registered a signal many times stronger than the normal levels of radio noise. The signal lasted for 72 seconds, rising and falling as it passed through the Big Ear's beam. No one was present to witness the event, but the computer system recorded the sudden escalation in signal strength, and the data printout clearly showed the tremendous spike in intensity. The moment passed, and Big Ear continued scanning the sky throughout the night.
There's nobody there typically to look at it, and then at that time, the computer, after it printed everything out, would be taken off to Jerry's house, and he'd look at it, and he'd look through that and see what he could find.
Computer records were delivered to my home about 2 times a week, a printout that contained 3 or 4 days worth of observations.
What you get when you're looking at data from a radio telescope is just a big ream of paper with numbers on it representing what the signals were at various frequencies.
When I would get home from teaching, or at night after supper, I would sit down with the computer printout and start to look for anything interesting. The data that included August 15th, 1977, and 2 or 3 days past that, just a few pages into that, I saw the pattern 6EQUJ5. And I saw, okay, the numbers are increasing, hitting a peak and then dropping off. That's exactly what we expect for a strong narrowband signal.
Since its discovery, there has been a popular notion that the WOW signal can somehow be decoded, that its alphanumeric sequence harbors some hidden meaning or message. In truth, the use of numbers and letters was a practical method for describing the intensity of radio signals observed by the Big Ear. The computer printouts generated by the Big Ear featured 50 columns, one for every channel being monitored. Each column had room for a single digit. Low-intensity signals were assigned a 1. Stronger signals were assigned a higher number. Because the printout columns were limited to single digits, signals stronger than a 9 were assigned a letter value, A 10 became A, 11 became B, and so on. This simple method clearly demonstrated the intensity of the wow signal. In purely numerical terms, the wow signal was 30 times higher than the lowest levels of random radio noise.
We tried to think of how could this be a fluke of some kind. It's the biggest thing we ever saw.
Within 10 seconds or less, with my red pen, I circled the 6EQUJ5 and wrote the word wow exclamation point. And it's fortunate, I got to thinking about this later, that wow was kind of like an expletive, but a good expletive, and so I didn't have to be deleted.
In searching for ET, the wow signal is the best candidate that's ever been seen.
The thing about the wow signal is that it had the characteristic shape, the change of intensity with time followed what you would expect from some transmitter that's up there in the sky moving with the stars. That's what made it so appealing, so different from the kind of normal interference that you get.
Amazed by the wow signal's intensity, Jerry Ehman continued reviewing the computer printouts from the night of August 15th and the days immediately after. He was searching for evidence that the incredibly strong signal had repeated.
I was especially interested to see if that same signal came back a day later, which would mean in the same position in the sky. It didn't. It didn't appear on the third or fourth days either. After I got through looking at all the printouts, I called Dr. John Kraus and said, "We've got something interesting here."
The wow signal presented many questions. Was it a natural celestial phenomenon? Could it have been a man-made signal from a passing satellite? Was it an artificial signal from an intelligent extraterrestrial civilization? John Kraus, director of the Ohio State Radio Observatory, and his assistant director, Bob Dixon, immediately began to investigate and eliminate the possibilities.
This is the scientific method. To discover something extraordinary, you need extraordinary proof. And so we wanted to eliminate everything else we could. And now interference is the common situation with radio astronomers. But we have interference all the time to the radio telescope, but we know what it is. We recognize it. We've done it for so long. We recognize it for what it is. And the characteristics of local interference, say, coming from the Earth, is totally different. Interference pulses on and off. It looks like a little static jumping up and down. Never does it follow the curve of the radio telescope like that, because what that means is the telescope was scanning across that area in the sky, and it went across whatever was sending that signal, and it went back down. It followed exactly the theoretical curve that it should follow for the shape of the antenna pattern of the telescope. That's another astounding piece of evidence.
Dr. Kraus did the bulk of the investigation as to what it could be. He looked at stars, galaxies, planets, satellites, and anything else that could have sent a signal, and didn't find anything.
Is it equipment malfunction? No. We ruled that out. Is it some planet or star or something? No. I mean, one could say it might be an Earth satellite of some kind, but the strikes are against that because we're using a frequency that's protected internationally for any transmitter. Nobody's allowed to transmit there. It's reserved for scientific research. So for a satellite to be transmitting there, they'd have to be disobeying that rule. But the fact is, if it's a satellite, it has to be moving in the sky. It would have to be moving at exactly the right rate. And that's just really not very practical to think about that. Is it a hoax? Well, Jerry and I are the only ones that could have pulled this hoax by fiddling around with the computer program. And I know I didn't do it, and I'm pretty sure he didn't do it. So we knew that it was there.
The Big Ear continued to search the same section of sky for 30 days following the wow signal discovery. Eventually, it scanned the area again for 70 more days. The signal never reappeared.
And what was even more puzzling is we actually had two beams in the sky at the time, slightly a few minutes apart from each other. And when it went through one beam, we saw it, and it went through the other beam, we didn't see it. So that means that the signal turned off at the time we were looking at it. And that's even more exciting because no natural signal would have done that.
The Big Ear design featured two large feed horns situated side by side near one end of the telescope's aluminum ground plane. The dual horns acted as funnels for the radio waves bouncing off the parabolic reflector, essentially giving the Big Ear two beams for observing and capturing data. After passing through one beam, a radio wave would be picked up in the second beam a few minutes later. The WOW signal's failure to appear in the second beam did cause excitement. It also caused ambiguity.
If we were to pick up the WOW signal today, you know, you would be able to, at least with some SETI experiments, you would be able to follow up right away. You would immediately start looking at it again. Now, you could say, yes, but they did that at Ohio State. They did. They followed up with one more observation. That was an automatic feature of the antenna they were using. So 2 minutes after they find the WOW signal, they've looked at it again, and that's it. But of course, today you would keep looking at it, keep looking at it, keep looking at it for, you know, minutes and minutes and minutes and minutes. And if you didn't find it, you would say it's probably interference.
In the years since its discovery, the WOW signal has been recognized worldwide as a significant event in the search for ET. Many still believe it's the best evidence to date of a communication from an intelligent extraterrestrial source. Others question its scientific validity.
The WOW signal certainly was a strong signal, right? There was no doubt about a signal being there. That's not the question. The question isn't, was there a signal? The question is, where did that signal come from? Did it really come from outer space? Did it come from something artificial? Did it come from something natural? Did it come from the Earth? And of course, nobody knows.
It remains unexplained. It was a highly significant signal that was unexpected and difficult to explain by natural phenomenon, but it was never repeated. It could never be verified. And so we're left really not knowing what caused it. You could imagine if an extraterrestrial civilization was intentionally trying to contact us, they wouldn't just send us one signal and then let it leave us hanging for, you know, many years wondering what that signal meant.
This is a movie of the galaxy M33. This came from the VLA in January of this year. What I'm looking for here is a big colored dot that's not always there, that's only in one radio picture at one frequency, which might be a radio signal pointed our way from the galaxy M33. No one's ever looked at this before. No one's ever seen this little movie I'm playing. This is what I called the small SETI radio telescope I built in the early 1980s. And this displays the direction the antenna is pointing, and this actually controls the antenna. So this 12-foot dish that's feeding electrical signals into this is being pointed around by a 1944 surplus military radar pedestal.
Where's the dish that you use with this?
The dish is outside. Watch your step a little bit. I first heard about the Ohio State WOW signal when I read an article about it in Cosmic Search magazine, a small radio astronomy magazine being published by John Kraus, the founder and designer of the Ohio State radio telescope. He wrote an article that described this unusual and intriguing signal that they discovered in 1977. I was a data analyst, a computer jockey, programmer at the time. This seemed so intriguing to me that I called the people at Ohio State, called Bob Dixon, I believe. Somewhat to my surprise, he didn't object when I suggested I'd visit Columbus, Ohio, and look at the radio telescope and the data personally. Everything I heard about the WOW signal seemed more and more intriguing, and more and more likely to be a real signal from the stars rather than interference.
Since the early 1980s, Robert Gray has been searching for the WOW signal. Like Grote Reber several decades earlier, Gray searched the sky using his home-brewed equipment and 12-foot dish antenna stationed in his backyard. Along with writing The Elusive WOW, which chronicles his searches, Gray has hunted the WOW signal at the Harvard-Smithsonian Astrophysical Observatory in Massachusetts, the Very Large Array in Socorro, New Mexico, and the Mount Pleasant Radio Observatory at the University of Tasmania.
The Ohio State WOW signal was only seen once. It was present for 6 10-second measurements, so it wasn't just a quick flash, but it wasn't seen twice for 72 seconds like constant celestial source should be. This is a flaw in the WOW signal, that it was only seen in one beam.
Some astronomers believe the WOW signal appeared in only one of the Big Ear's beams because it was man-made interference, or perhaps some sort of natural anomaly. But an opposing school of thought suggests another possibility. A radio signal from an intelligent extraterrestrial source might appear intermittently.
It's possible that the WOW signal didn't show up in the second horn because it was some kind of sweeping signal, like a cat's eye beam of a transmitter that was sweeping across the sky and swept across the Ohio State beam in merely a few minutes. Most people involved in searching for extraterrestrial intelligence have one of two scenarios in mind. One is a beacon that's shining all the time. So anytime we happen to look at a certain spot in the sky, we'll see it, if we're tuned to the right frequency. That's a terribly expensive thing to do. The amount of power is way more than all the power on Earth to operate a beacon that shines in all directions all the time. The other scenario is a big antenna that points our way every so often, a directed beam, and that uses a lot less power. That's the reason why big radio telescopes are so big, is that they see a smaller spot in the sky. And for a transmitter, that means that they're only shooting the power towards a small spot in the sky. So you need a lot less power. The drawback to a directed antenna pointing at us is it's probably not going to be pointing at us all the time. That's another possible explanation for something like the WOW signal being intermittent.
Despite his continued searches and long-term effort, Gray has not been able to find the WOW signal again.
As far as I can tell, having talked to nearly everyone in the field, no one else has ever looked for it. No one except for me has tried to follow up on it. And my observations are admittedly those of a non-professional and might very well have had some flaws. The professional astronomical communities never really looked hard for this thing. It might be worth doing so.
People will ask me at parties when they hear what kind of work I do, they say, well, are you close? You know, I don't know what that means. Are you close? Because until you found a signal that you can verify, and that is clearly extraterrestrial in origin, you've not had any close calls, you've not had any successes, you've been looking. It's like, you know, Captain Cook in the South Pacific in the 1770s, right? Every day he just sees more water around the ship, and, you know, so, well, are you close? Well, he doesn't know whether he's close.
As a senior astronomer for the SETI Institute, Seth Shostak has been an active participant in the Institute's SETI observing programs. He has written and lectured extensively about the search for extraterrestrial intelligence, including the WOW signal.
The WOW signal, of course, continues to intrigue people, and maybe people think that it's our best case for a signal from extraterrestrial intelligence. I find that maybe a little bit I don't know, overstated to say it's our best case. It's an intriguing case because it's a mystery. We don't know what it was. But then again, if you look back into that era in the late 1970s, there were other SETI experiments running as well, and they would come up with mysterious signals as well. They would come up with signals that were seen only once and that had the hallmarks of the kind of signal you're looking for. But they didn't have the great name wow signal. They were just sort of anonymous signals coming from a certain spot on the sky. I've written occasionally about a signal that we picked up in 1997, which was to my mind, the most interesting candidate signal that we've ever gotten. And for most of a day, it looked like it was the real deal. Turned out it wasn't. It was due to a solar research satellite, a European solar research satellite. SOHO is the name of the satellite. But for about 16 hours or so, we weren't sure. We thought it might be the real deal. And that was actually a very interesting event. It was a good thing it happened in my mind because it showed us what happens if you actually pick up a signal that is what you're looking for. The wow signal may be a case of the triumph of branding over product, perhaps.
Whether it's the best case of a signal from ET or an unintentional triumph of branding, the wow signal may be the most widely recognized event in SETI's short history. In the years since the wow discovery, SETI experiments have continued, benefiting greatly from advancements in technology and more sophisticated search techniques. Still, there are those who feel we have barely scratched the surface.
It's hard to describe how modest our searches have been so far. We've typically only looked for a minute or two in any one direction and any one frequency. It's entirely possible that there's beamed transmissions pointed at us from other stars that if we happen to point a big antenna in the right direction, tuned to the right frequency, we would hear. We simply haven't conducted a long enough search yet at enough different frequencies to even know if that's possible.
Most SETI experiments, you spend very little time looking at any given direction at any given spot on the radio dial. Seconds, minutes, no more than that. And you might say, well, that doesn't sound like a very good strategy. Maybe they do broadcast in our direction, but only once a day, or once a week, or once a year. You're going to miss them, most likely. And that's true. But if you're doing this experiment, you have to decide what's the better strategy. Are you going to use that time to just keep looking in the same direction at the same frequencies, or are you going to look at another star system? It could be that somebody is not incessantly targeting the Earth, because after all, they probably don't know that Homo sapiens is here, right? Unless they're within 70 light years, they haven't picked up the kind of radar or FM radio or television signals that would betray our presence. They know there's life on Earth because of the oxygen in our atmosphere, but they don't know that there's any intelligent life. So, how much money would you spend to relentlessly target some other planet with a signal if all you knew was that it had biology? Maybe all it's got is microbes. That's the situation that obtained here for a couple of billion years. So, maybe you don't spend a lot of money there, but maybe what you do is you have a long list of all the planets that have life, and you just target them all sequentially. You give them a quick ping, right? You give them a ping, and then you come back 2 weeks later and you ping them again, or maybe 2 years later or 200 years later. And you just ping them occasionally and see if anything happens. And the wow signal could have been a ping. That's certainly a suggestion. That's just one possibility. There are many possibilities. And unfortunately, that doesn't turn it into science until you can prove that one of them is true.
Scientific opinions continue to differ about the origin of the wow signal. Even with the controversy, it remains an extraordinary event in the broader search for extraterrestrial intelligence.
I think probably the majority of astronomers think that it was just some naturally occurring phenomena that just happened once. We're left really not knowing what caused it. We can't really be sure that it was an extraterrestrial civilization. SETI is based on the presumption that we are not the only civilized society in the galaxy, and that there are civilized societies in the galaxy that are willing and able to communicate with us. There are two primary paths by which we are looking for life in the universe. One is a systematic, more scientific path. The first step that you might want to know is, well, are there planets around other stars at all? Then if you know that there are planets around other stars, the next thing you might want to ask is, well, do those planetary systems look anything like our own? Once we find some solar systems like ours, then what we really want to look for are planets like the Earth, pale blue dots. So those are rocky planets with thin atmospheres, located at the right distance from their parent star where they can have liquid water on the surface. And that's a lot of the way in which we go about science, is we take one step at a time. We build upon previous advances in knowledge till we ultimately get to the final question that we want. SETI, on the other hand, is kind of like taking a novel and going back to the last chapter and reading that and finding out what happens. It's kind of cheating in some sense. It's not going through the whole book. So you're just trying to look directly for intelligent civilizations immediately without having to go through all this systematic process of leading to the discovery of life. The opinions of SETI in scientists that are searching for life range from it's a crazy thing to do to it's a reasonable thing to do.
SETI is only for patient people, because you can search a lifetime and never find anything, but it's still so interesting and important that you always do it. So that's why people like Jerry and I get involved in doing things like this. The big danger in SETI is called anthropomorphism, looking at things from the viewpoint of man, because it's the only way we can. We try not to think about specific signals, but look at general signals, which are narrowband, which would be characteristics of any such signals.
I think that the wow signal, even though it couldn't be identified, couldn't be verified, was a kickstart to the continued search for extraterrestrial intelligence. I mean, you think about even a young scientist, a young astronomer, who is trying to decide what his path or her path may be. You read something about the wow signal, and it gives you a whole new door to open. It gives you another possibility.
We're looking for something that we don't know is there, or if we're going to ever be able to detect it. And that's, a difficult thing to justify. But it's also potentially one of the most important questions, we ever want to answer. So you have this balance of something that's very high risk, but very high gain.
The search for extraterrestrial intelligence, I think it's fair to say, to some extent, has had a stigma associated with it.
The perception of SETI is the UFOs and sightings, that little green man with big eyes. And it's been potentially difficult to shake off that association.
There's an entire culture of people that believe in UFOs and that we have in fact been contacted by aliens many, many times.
Of course, there's a lot of excitement around the idea of aliens, of SETI, of any of that, because how could it not be just incredibly exciting to think that there is some other race out there, some other very exotic type of race out there in the universe, and the idea that, hey, we'll be able to interact with them is just really, really enticing and really, really exciting.
We get a lot of UFO reports at Perkins in one form or another. And I have to say, it's always, always, always some natural event. There was one thing that I saw one time, I had no idea what it was. These beautiful white points of light darting around. There were just a whole lot of them. So I got in my car and I drove toward it. What was it? It was a bunch of seagulls dancing around a billboard. The billboard lights tend to point up, and it was the lights reflecting off their stomachs. Thought I had it, but it was seagulls.
The sensationalism that surrounds SETI research can be pretty amazing, and Greenbank has not been immune to it. When the 300-foot telescope collapsed in 1988, there were, albeit tabloid, newspaper headlines that said, "Aliens destroy radio telescope in Greenbank." That's just proof of, you know, the need for people to think about the fantastical, to be exposed to the fantastical.
If somebody could come up with one thing, one time, that they could describe to me that I couldn't figure out what it was, then I might be more interested in this kind of thing.
Human beings love to wonder why. Other beings out there in the universe is just so tantalizing, so exciting to think, you know, there's something else out there. We're not alone.
As a skeptic, as a scientist, I'm a skeptic, and as a skeptic, I have to say that I don't believe there's been any real definitive evidence of extraterrestrial life contacting us. Of course, which begs the question, does that mean that such life is rare? A lot of people are familiar with the Fermi paradox, which simply put is if intelligent life is out there, why? Where are they? Why haven't they contacted us? There are various solutions to this apparent paradox, but one of them is simply that there is no other intelligent life out there, that we are the only intelligent life in our galaxy. If I were a betting man, and I'm not, but if I were, I would bet that simple life is probably fairly common, and we will probably find it, maybe not in my lifetime, but certainly within the next few hundred years.
One of the problems with SETI is that you can't guarantee success. If you decide that, you know, as a young astronomer, you're going to go study exoplanets, you can be sure you're going to find some. You're going to learn something new. You can't miss. We found thousands of exoplanets, so of course you're going to find some. With SETI, there's no guarantee. It may be that you spend, you know, decades, maybe this takes centuries, maybe more, who knows, to find something. And all that time you didn't find anything. And you got to be able to take that. You got to be able to say, look, I'm down with that. I can handle that.
I personally feel that it is entirely possible that we will discover life beyond our own. Can I definitively say that it's going to happen in my lifetime? No, I can't. Do I think it will happen? I absolutely do think that it'll happen. I do believe that there's life elsewhere beyond our planet. How advanced that life may be is a question, but you know, certainly if we have progressed to the level of intelligence that we are, and some argue that, well, maybe we aren't either, I can't imagine that other potential life forms haven't progressed far beyond where we are.
Will we discover life that is beyond just the cellular life and moving on to something that is intelligent? Boy, you know, it's such a guess. We might.
I think you have to be honest with people from whom you are asking for funding. The difficulties are great here, and the chances of success are very limited. And you probably won't find anything.
Funding of basic research seems to be a challenge, especially in this day and age. We can't say that we're creating anything. We're not building widgets. We're not selling something for retail. We're doing basic research. And basic research sometimes is a hard sell. Americans like a result. You know, they like something they can hold in their hands.
Careful. There's a tag in there, it's just
Is that
loose.
Einstein right there?
Yeah. Ever since 2012, the observatory has faced some issues in terms of decreased funding.
As the first national radio astronomy observatory in the United States, Greenbank had always been fully funded by the National Science Foundation. But changing federal priorities created funding challenges over the years. In 2012, the National Science Foundation recommended a gradual defunding of the Greenbank facility.
You know, the potential is there that one of the options is dismantling the telescope. You know, we disappear, and the research that's done here at Greenbank could disappear.
There's nobody I'm aware of that would like to see Greenbank close. And I mean that all the way up to the people that are making the funding decisions to cut back our funding. They really don't want to see this place closed. Nobody wants to see this place closed.
While the observatory could find other collaborative parties which could provide funding, the problem with that is the NSF provides open skies science, which means anyone can come in and apply for time, whether they have the money or not. That is a really important thing to keep going. We're just going to try and do what we can to help keep that secured. The Greenbank Observatory has had more impact than I can say on my future and my ideas of what I'd like to do. Aspects of astronomy that I was not familiar with. For example, I've gotten so interested in the instrumentation side. I just think it's really important to have that background in knowing your equipment and knowing what you're researching so that you can do things like compare, is this an actual signal or is this some sort of system issue, which I think is really important in SETI as well as in every field of research in radio astronomy.
When I first met Ellie White, her and her mother came into my office. She was about 11 years old. And the funding problems for Greenbank Observatory had sort of just been released. And Ellie had been, in her own time, creating these cloth dolls of scientists. So she picked her favorite scientific people from history. And she had a Madame Curie doll, and she had these others. And the purpose of her visit was to see if we might want to sell those in our gift shop, which I thought, well, that's kind of cool. Maybe we could do something with her. But what she said next is what I'll never forget. It'll be one of those moments that will live with me well after I'm retired. The reason that she wanted to sell them in our gift shop is because she wanted to give part of the proceeds back to the observatory to help fund our mission.
So these are two of the scientist dolls. This is Nicholas Copernicus and Albert Einstein. I started showing them to people and they said, you should sell these. So I thought, well, I'll sell them and donate part of the profits to Greenbank.
How appreciative have they been about these dolls?
Very. They're very appreciative, and just it's great to hear some of the stories of people who come in and buy them. I think the first doll that was sold was to a lady from New Zealand.
Will you keep doing this?
Yeah, as long as I can keep up with the demand.
Greenbank has had such a profound effect on her. Just the exposure to what we do here changed her completely. She became so passionate about astronomy, so passionate about protecting the Greenbank Observatory, to make sure that other people get the same reaction, get the same effect.
This has been a life-changing experience for Ellie, for Josh, my son, for us. She's learned things about how to ask questions without fear, to have curiosity and enthusiasm about learning, which is really what we're all striving for, and that's what we look to the heavens for.
Ellie's passion for science and for astronomy is amazing, and it's just really neat to watch. If we were, heaven forbid, to stop funding fundamental science, then I think we lose a lot of things. I think in the near term, we lose a little piece of humanity. I think we lose a little piece of our ability to just go ask the question why and try to understand who and how we got here. And then in the long term, if you don't have people doing the basic fundamental research, you're not going to have big breakthroughs 10, 20 years from now in understanding everything. And to me, that's the most important part of all this.
It's time to commit to finding the answer to search for life beyond Earth. The breakthrough initiatives are making that commitment.
Breakthrough Listen takes the search for intelligent life in the universe to a completely new level.
In 2015, Russian billionaire Yuri Milner, along with Stephen Hawking, Frank Drake, and others, developed a long-term initiative dedicated to the search for intelligent civilizations beyond Earth. The highly funded SETI project, known as Breakthrough Listen, required the world's most powerful radio telescopes, including the world's largest fully steerable scope at the Greenbank Observatory. Much like Ohio State's Big Ear telescope many years earlier, Greenbank's path led to the search for extraterrestrial intelligence, and the opportunity came at the perfect time.
It's interesting how the timing of these things works out. The GBT and the Greenbank site were in need of finding external sources of funding. The Breakthrough Listen program is a privately funded project over 10 years with $100 million being spent on it. It is the next huge modern search dedicated to extraterrestrial intelligence detection. They needed to utilize the best technology that they could find. And the GBT, the Greenbank telescope, is a radio telescope that can give them more sensitivity, more sky coverage than any other radio telescope in the world.
The search for extraterrestrial intelligence has been going on for more than 50 years now. With the advent of Breakthrough Listen, 20% of the Greenbank telescope's time per year is dedicated to the search for extraterrestrial intelligence. And that is hundreds of hours, much, much more time and resources put towards SETI. So I think that really ups your chances.
Would we like to actually see a signal in there? Of course, it would be amazing. It would change the way we would look at the universe, because it's one thing to say there might be a signal out there. It's another thing to say we have found a signal out there.
Greenbank is searching for its own wow signal. We are looking for the signal that's going to knock our socks off, and we can't wait till we find it. Why would we ever want to give up the capability to expand our horizon and go back to a level where even the most basic question about our universe has to go unanswered because we didn't put $1 into it? If the GBT or the Greenbank Observatory were to disappear, it's gone. These are national treasures located all around this country and some located around the globe that we just don't want to give up. The amount of money that it takes to run them is minuscule compared to the potential for expanding our knowledge that exists because they are here.
So what are we looking at in here?
We're coming to the Big Ear room. This is a room that we created in honor of the Big Ear, and we made copies of the wow signal, the data that we call the wow signal. And we had built a beautiful scale model of the telescope, the Big Ear telescope. Imagine taking this element right here, the collector, and moving this enormous metal structure up and down so that you can collect information from different parts of the sky than, say, straight up.
Can you take us out to the Big Ear?
Sure, let's go. That just happened, of course, and we'll get that out of there eventually. Eventually. I come back here practically every day. Big Ear is just over the crest of this hill. Oh, I hate to walk on a golf course in my street shoes, but what are you gonna do? Ladies and gents, Big Ear.
After losing federal funding in the 1970s, the Big Ear telescope shifted to the search for extraterrestrial intelligence. Besides discovering the historic WOW signal, the Ohio State SETI program was recognized by the Guinness Book of World Records for running the longest full-scale SETI program for its time. In 1997, despite its contributions to radio astronomy, developers decided the land under the Big Ear would be better served as a housing development and golf course.
We got word that the land had been sold out from under us without even informing Dr. John Kraus or anybody. They simply sold the land to land developers, and their goal was to increase the size of the golf course from a 9-hole course to an 18-hole course, and then to build some 400 homes on the land. Just a few months before John Kraus died at age 94, he decided he needed to write a little notes expressing this as a day of infamy, the day that he received notification that the Big Ear was going to be torn down.
That caused a great hue and cry, and Ohio State University said, we are not going to spend money with lawsuits fighting over developers, so they threw in the towel.
Had they had a well-financed research program going, I think they might have survived. Unfortunately, a lot of these major scientific instruments get superseded. They become obsolete. Interest of science, scientists, and science funding agencies moves on.
The Big Ear had its day. It did important research in astronomy. It did that SETI research for all of those years. But there comes a time when old technology simply has outlived its usefulness, and with sadness, you tear it down. It was a sad moment to see it go, but the simple fact was that it had outlived its usefulness. It had its time in the sun, and the land was useful for other purposes.
Do you think a golf course and housing development, do you think that was useful?
Well, the fact is that before the Big Ear came along, the land was basically just wasteland. It was covered with trees and brush. And of course, the Big Ear really wasn't good for much anymore. The simple fact was, it was frozen in place. You could no longer remove the main primary light gathering device up and down like this, so it was frozen in place like this. So that what they essentially had to do was to wait for the sky to rotate above them if they wanted to collect information on a given star or from a given star to do SETI research.
People miss it?
I would say there was a giant uproar when the land was sold. But by the time the Big Ear was finally torn down, people weren't so upset about it.
Is the Ohio State Observatory an icon, a temple of science that shouldn't have been demolished? It accomplished a lot, but I don't think it was an icon. Unfortunately, if it turns out the WOW signal is a real thing, that sometime, somewhere down the road, somebody demonstrates that it's an interstellar broadcast, it'll be tragic that the Ohio State radio telescope was torn down.
If the WOW signal had been verified, if it had been found again, then it would be in every history book in the world. That would be one of the most important discoveries of all time. And because of the fact that it has this wonderful name, Jerry Ehman was really brilliant to write WOW next to it. If he just made a check mark, probably nobody would have ever heard of the WOW signal. At least the public probably wouldn't have heard of it. So You know, that's the difference between a confirmed result and an ambiguous one, unfortunately.
Why do we search? The road is long, with few rewards. The skepticism demanded by good science tempers our excitement, and discovery remains elusive. And yet, we persevere, fascinated by the possibility of what could be.
Why care about life elsewhere? That's a good question. Life here is a riot of different forms, colors, sizes, noises, environments, behaviors. And I think that people probably have an innate interest in whether something like that happened elsewhere. And the only way to settle that question, of course, is to go look.
I do think there is extraterrestrial intelligent life. And more than one instant in our galaxy and certainly in our universe.
The universe is so vast, and the Earth and the Sun are not unique in any way that we know of. There are literally millions and billions of other planets like the Earth. It just seems scientifically improbable that life would have emerged only here. But on the other hand, someone has to be the first. So maybe we are the first. If so, it gives us a greater responsibility to say, all right, we're the first. We better not destroy ourselves. We better populate the universe and make things better for everyone and not blow ourselves up in some stupid way.
We desperately want meaning of some sort. We'd like to know why we're here. Are we here just by random accident, or were we here on purpose? We are trying to find context to our humanity.
It's really hard to predict what the consequences of finding a signal proving that we're not alone, what consequences that would have. This would be a sort of an inflection point, a change in human civilization, because we would know that somebody's out there. If we could ever understand any part of the signal, that might change us much more, because you would suddenly be privy to knowledge that's most likely far more advanced than our own. So, you know, that could change everything.
Think of the impact of it. The entire world would be transformed when each and every person on this planet realized that we are not alone. We live sometimes in a difficult, ugly, violent world. And you're looking for some solace from that. And the one thing that this search for extraterrestrial intelligence gives you is that kind of hope. We want this. We want that sense even more that we are capable of escaping the tyranny of the gravity that holds us, that we can soar outward into the universe. And where do we find that? In the hope, the faint hope, that other civilizations have survived their crises and been around for long enough to be able to soar themselves. We're lonely. We want that sense that we are not alone. We want it so badly.